Hi, welcome to the next lecture in the NPTEL course on Haskell. In the previous lecture, we saw merge sort, and we even saw how much of a difference in time it is between merge sort and insertion sort. Let's continue discussing merge sort and actually working out the an estimate of how much time merge sort takes. Recall that merge sort is the following procedure: divide the list into two equal parts, separately sort the left and right half, recursively merge the two sorted halves to get the full list sorted. And I'll just go through the example of merge again. So how do you merge given two sorted lists x's and y's? Merge it into single sorted list z's as follows: compare the first element of x's with the first element of y's, and move whichever is smaller into z's, and you keep repeating this until all elements in x's and y's are processed. Okay, this is the informal description. Here is an example. If I have 22, 32, 43, 78 and 13, 57, 63 and 91, I will compare 22 and 13. 13 is smaller, so that goes here first. And you continue with merge 22, 32, 43, 78 and 57, 63, 91. Now compare 22 and 57. 22 is smaller, so you get this, and you will end up trying to merge 32, 43, 78 with 57, 63, 91. You will compare 32 with 57, 32 is smaller, so you will get this, and it keeps on going, right? So then you will compare 43 with 57, 43 is smaller, so it goes here. Now you will compare 78 with 57, 57 is smaller, so this 57 goes here. Okay, now I will compare 73, 78 and 63, 63 goes here, and 78 goes here, 91 goes here, etc. Right? So this is how you merge. And if you want to do merge sort, you sort separately, you sort the half of the list that from element 0 to element n by 2 minus 1, you sort that, and then from element n by 2 to element n minus 1 you sort, and recursively using the same procedure as we saw. Whatever you want to do for L, you recursively do the same thing for the front half and the back half, and you merge the two sorted halves into a single, not into L but into sort of L. How do you sort the halves? Recursively using the same strategy. Okay, so now we saw this example of sorting in the last lecture, but I will go over it again. Sorting 43, 32, 22, 78, 63, 57, 91, 13. So you will split the list into two halves. So you sort the first half, sort the second half, and then merge. Yeah, but that would involve sorting. Sorting the first half would involve sorting the first half of the first half and the second half of the first half. So namely 43, 32, 22, 78, and then you merge them. Similarly, 63, 57 you sort, 91, 13 you sort, and you merge them. But sorting 43, 32 is nothing but sorting 43, sorting 32 and merging them. Similarly for the other lists, but sorting a singleton list is just that singleton list. So you will end up with merge 43, 32, merge 22, 78, merge them, merge 63, 57, merge 91, 13, merge them, and then merge the two lists like this. So you will see that it's a, you will bring it all the way down to some singleton lists, and then you will keep merge. Okay, that is the point. Okay, merge of 32, 43 and 22, 78, and then merge of 57, 63 and 13, 91. So merge of this is 22, 32, 43, 78. Merge of this is 13, 57, 63, 91. Now you merge these two, you will get a final sorted list. And here is the algorithm for merge. Merge itself is just this: merge of empty list y's is y's, merge of x's empty list is x's. Merge of x followed by x's and y followed by y's is, if x is less than or equal to y, you do x followed by merge of x's, y followed by y's. Otherwise, it is y followed by merge of x colon x's and y's. And the time taken for this is order n, where n is the sum of, n is length of x's plus length of y's. Okay, and sort itself is the following: sort of empty list is empty list, sort of singleton x is singleton x. Sort of x's, you first calculate n, which is length of x's div 2, and then you split the list at n. So you will get a front portion and you will get a back portion. Sort front, sort back recursively, and then merge the two. This is the algorithm for merge sort. That was the basic idea, and you can see how easy it is to just transcribe it into a bunch of equations which turn out to be actually a Haskell program. Okay, you're just saying what does it mean to sort singleton list? It is just the same list. What does it mean to sort x's? You have a strategy in mind, and according to that strategy, sort of x's is nothing but merge of sort the front half and sort the second half. You just write it out. That's an algorithm. That's a program actually which compiles and runs. We already saw how it runs. Let's look at the time taken by merge sort. Okay, so let's denote by Tn the time taken by sort on input of length n. You will see that let's assume for simplicity that n is a power of 2. This is not really a problem because you can always find the next power of, so if I have a general n and if you find the next power of 2 after n, it is not, so yeah, so for any n, we can find a power of 2 in the range n to 2n minus 1. Yeah, so it's not a problem at all. You are not overestimating or underestimating. Finally, we are going to just give some order n kind of time complexity, and it doesn't matter whether you think of it as n or 2n. Okay. Okay. So if you assume that the n is a power of 2, then the lengths of front and back are n by 2. There are two recursive sorts. So, and overall the time taken by length to compute the length of a list, remember you have to do some work. Length of empty list is 0. Length of x colon xs is 1 plus length of xs. So length takes time order n. Splitat takes time order n, because remember splitat of n x's, if n is less than or equal to 0, you are just going to say if x's is null, you are just going to say splitat is this thing. You don't care what n is. Now, if n is greater than, or if n is actually greater than 0, and if xs is also non-empty, then splitat n xs is so in fact I should rewrite this. So the way I will rewrite it is as follows. Splitat anything empty list is empty list empty list. Splitat n x colon xs is else it is x followed by else you have to do the following. Let front and back be splitat of n minus 1 of x's in x colon f followed by b. Okay, so this is splitat. Okay. So, right, and now you will see that if I want to split at n, I will make one recursive call which is split at n minus 1 all the way till I get to 0. So, if I want to split at n, the amount of time I will take is order n, but here in our example what we are doing is we have a list of length n, and we are doing split at of n div 2 of x's. So, the time taken is roughly order n by 2, which is the same as saying order n. Okay. So, and merge, as we saw, takes time order n. So, overall the time, if you sum all that up, you will still say that all these things together take order n time. Okay. Okay, good. So, let us assume when I say order n, it is some constant times n. So, it could be any constant, it could be 100, it could be 200, let us call it c, okay, for some constant c. So, my recurrence now for t of n is 2 times t of n by 2 plus cn, okay, and we have to solve this recurrence. This takes a little bit of work, but it is nothing really fancy. You just need to do some basic unrolling the recurrence and recognizing a pattern. That's all we need to do, and we don't require any more mathematics than high school mathematics for all this. Okay. So, t of n is 2 times t n by 2 plus cn, t of n is 1, t of n is 2 times t n by 2 plus cn, but if I want to expand this t of n by 2, that will be 2 t n by 4 plus cn by 2, okay, which is what I have written here. But now I can multiply the 2 inside and it will become 2 squared t 2 n by 2 squared, I will write 4 as 2 squared, plus 2 into cn by 2 is cn, plus I have a cn there, so it will become 2 cn. Yeah. So, let me just expand this a little bit. This will be 4 t n by 4 plus 2 into cn by 2 plus cn, that is 4, instead of writing it as 4, I will write it as 2 squared t n by 2 squared plus cn plus cn, but 2 t squared 2 n by 2 squared times t of n by 2 squared plus 2 cn. Okay. Now, if I expand t of n by 2 squared again, it will be 2 times n by 2 cubed plus c of n by 2 squared, but I am multiplying it with 2 squared. So, once again I will have 2 squared multiplied by cn by 2 squared is just cn. So, that will contribute an extra cn now, and this thing is 2 cubed into t of n by 2 cubed. So, now I will get 2 cubed into t of n cubed n by 2 cubed plus 3 cn, and you can keep on going like this till at some general point you will have, in general you will have 2 to the power of j times t of n by 2 to the power of j plus j cn. This would be your equation. Let's try to let's see how to simplify this even further. That is my recurrence, and I have expanded it to 2 to the j t of n by 2 to the j plus j cn. Now, when would this t of n by 2 to the j get simplified? It will get simplified if n by 2 to the j is equal to 1, then t of n by 2 to the j is equal to t of 1 equals 1. But when would n by 2 to the j equal 1? This would happen if n is equal to 2 to the j, or in other words, j is log to the base 2 of n. Okay, this is the point. When j is log n, 2 to the j is equal to n, and n by 2 to the j is equal to 1. Therefore, I will have 2 of n is 2 power log n times t of 1 plus cn, instead of j I will put log n. Right now, this is nothing but 2 to the log n is n times t1 is 1, so that is n. So, it is n plus cn log n, which I can summarize as saying order n log n. Okay. So, in summary, merge sort takes time order n log n. Okay. Good. So, this is important. In case you are wondering where n log. So some of you might have already known this fact that merge sort takes time order n log n. You might even know some other sorting algorithms or some other algorithms that take times which involve some log. Here is exactly how the log comes about. Okay, so you just write a recurrence which is just like a recursive equation. Your function was recursive, so the equations for the time taken will also be recursive, and then you try to eliminate the recursion by unrolling the recursion and then figuring out a pattern. Usually we will just see some simple patterns and then simplifying it further. Okay, so merge sort takes time order n log n, and that is why you saw the difference in time taken between merge sort and quick sort for that random for that list of length 10,000, because notice that if I have 10,000, what is log n? Log to the base 2 of 10,000. Okay, so let's try to estimate. So I have 2 to the power 10 is 1024, and 2 to the power if I multiply this by 16, 16 is 2 to the 14, right? So then that would be 16,000 something, which is greater than or equal to 10,000. Okay, so roughly log to the base 2 of 10,000 is 16, let's say. So your merge sort on list of length 10,000 takes time, takes number of steps is around 1,60,000, right? Whereas insertion sort is around 10,000 times 10,000, right? You can see how much of a difference it is, right? It's one takes 16 times 10,000, the other takes 10,000 times 10,000, and that's why you see the difference. If you increase the numbers, the difference you will see will be even more dramatic. This goes to tell you that if you want to improve performance, you have to actually rethink sometimes and get a, it is not enough to just be clever with your programming, you have to actually come up with a completely new idea and a completely new algorithm. Okay. So let's try to improve this merge sort. I mean, as good as this merge sort was, it performs much better than insertion sort, but still the algorithm was a little wasteful, because if you recall, sorting for 43, 32, whatever this list is, I have to sort the first half, sort the second half, merge them. This itself involves sorting the first half here, sorting the second half and merging them, but that involved this sorting this half involves sorting the singleton list 43, the singleton list 32 and merging them. Sorting the singleton list is nothing, sort of a singleton list is nothing but just that singleton list. Eventually you have this, you have the singleton list 43, the singleton list 32, here, here, and then you have a tree of merges. You can imagine that you have your original list, let's say 10, 8, 7, 15, 22, 33, something like this. You are forming singleton lists out of these, and then you are saying, oh, merge these, merge these, merge these, merge these, there is nothing to be merged there, and merge these. Okay, so it's a tree of merges. And singleton lists at the leaf, at the leaves, right? Because if you merge these two, you will get 8, 10. Merging these two, you will get 7, 15. Merging these two, you will get 7, 8, 10, 15. Merging these two, you will get 22, 23. And merging these two, you will get 7, 8, 10, 15. Right? So what is really happening is merge, repeated merging, okay, starting with singleton list. So why do you need to unnecessarily have this sort programmed like this? Okay, so we can actually do better. So you can create a list of singleton lists from the original list and repeatedly merge adjacent pairs till we are left with a single list. Okay, that's all. So singles will actually take you from the list x1 dot 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 xn to the list consisting of singleton lists. Okay, and map the colon empty list operator applied on any number to, let's say, takes you 2 colon empty list, that is nothing but singleton list 2. Okay, so the colon empty list is an operator that turns a number into a list, and you can therefore map the colon empty list partially applied operator. Colon, remember these are sections. Colon is the operator which you apply it on some x and x's will give you x colon x's. Okay, colon, if you apply it on x and empty list, will give you x colon empty list, which is nothing but the singleton list x. But if you are fixing the second argument, then you can actually write it as colon empty list applied on x, and that would be nothing but x colon empty list is. So colon empty list is the operator that turns numbers into, or whatever elements, into lists. So you map your original list, you map the colon empty list operator on each element of the original list. Okay, and then what we said was merge adjacent pairs. Okay, so if my list consists of, if my list is empty, remember this is a list of lists. Merge adjacent lists in a list of lists. Okay, so if my list of lists is empty, then my output is also empty. My list of lists consists of a single list L, then my output is just that single list L. But if I have two lists, L1 followed by L1, L2, then followed by some other list, then I'll merge L1, L2, and then I'll merge pairs of Ls. Okay, so what happens is that if I have something like I don't know, 1, 2, 3, 4. This will, if I do merge pairs, I will get the list 1, 2, the list 3, 4, and the list 5, 6. Okay, so originally I had a list consisting of 6 lists. Now I have a list consisting of 3 lists. I can again do merge pairs here. Now I will end up with a list consisting of 2 lists. I will again do merge pairs here. I will end up with a list consisting of 1 list. At that point, I have merged everything in my original. I had lots of singleton lists and I have managed to merge all of them. So I can just return it. Okay, so merge all of an empty list is empty list. Merge all of a singleton list is just that list returned. Okay, and merge all of x's is merge all of merge pairs of x's. Right. So merge pairs will take you from. So in fact, rather than calling it x's, I will call it L's. Merge pairs will take you from one list of lists to another list of lists. It will take you from here to here. If I have singleton list 1 followed by singleton list 2 followed by singleton list 3 followed by singleton. If I have something like this, these two are merged and that becomes this, these two are merged and that becomes this, these two are merged and that becomes this. Originally I had a list consisting of 6 lists, now I have a list consisting of 3 lists. Okay, merge pairs take you here. Merge all will now repeat this same procedure. It will again apply merge pairs, etc. till you finally get a list consisting of a singleton list, at which point you will just return that list. Okay, so merge pairs, if you want to be very clear, merge pairs is of type list of int to list of int. Merge all is of type list of int to list int. Because at this point, if I have a singleton list consisting of a list L, I will return just that list. Okay, not the list consisting of L. Okay. Finally, sort is nothing but first create all singleton lists and then do merge all. That's it. So recall that I had this merge tree starting from singleton list. That is exactly what you can do with sort. Okay. you can actually re-express sort as this, okay, create singleton list, merge all, okay, and the time complexity doesn't change at all, because even originally the time complexity was all the time complexity of merge. In fact, it's better because you don't need to apply length or split at or any such thing, okay. So you save on the intermediate time you do to compute length and split at, etc., because you're directly doing this map of this colon empty list will take order n time, and at each level merge will take order, whatever the order, merge will take time proportional to the number of elements in the merged list, okay, and that's basically it. Okay, so we can actually program this and see. Here you might not see so much of a time difference as between insertion sort and merge sort, but you might, with some complicated examples, you might still see the difference. Yeah, some random list of 1000 elements, and merge sort is able to sort it. Okay. I've also programmed this this thing, as you can see, singletons is what I'm calling singles. It's map of colon empty list. Merge pairs is just what I told you. Merge all is just doing this, and msort prime, because I already have an msort, is merge all dot singletons. Okay, so first compute singletons and then run merge all on them. Okay, that's this, and I'll copy this into my file. I can copy this into the sorting.hs that I have. Let me reload the thing, and let's once again create a new some random list of length 1000. Let's see what is excess. Okay, some random list, msort of excess, take some time, msort prime of excess. It's slightly quicker, but if you programmed these on your own machines, and if you actually try it on longer lists, you will see a slight difference in time. Okay, msort primes performs much better. You can actually improve it even further. Let me go back to the slides and I will show you further improvements. So singles, okay, so first time analysis, singles takes time order n to transform the list x1 dot 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 xn to singleton x1, singleton x2 dot 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 singleton xn. Merge pairs on a list L1 dot 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 LM takes order K1 plus K2 plus dot 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 KM steps, where yeah, so that's clear, because to merge L1 and L2 you require length of L1 plus length of L2 times. I am assuming that right, merging L1 and L2 will take time K1 plus K2, merging L3 and L4 will take time K3 plus K4, and so on, right. And merge pairs will reduce a list with reduces a list with containing m singleton m lists to another list consisting of m by 2 lists, right. So after order log n recursive calls of merge all, you will end up with a list consisting of a single list. Yeah, so after order log n recursive calls of merge all, the list of singletons will reduce to a list consisting of a single list. Okay, so list of n singleton lists to singleton list whose element is an n length list. Okay, and then you just return that list which is inside that singleton list. Okay, L prime is a L in sorted order because all we have done is just take the singletons and keep merge. Thus, the overall time taken is order n log n, because every time you need to do merge pairs, it does not matter what it is, it's merge pairs will take time proportional to the length of the sum of the lengths of all the internal lists, that is all, and the sum of the lengths of all the internal lists is n. So, every time you do merge pairs you take time n, and overall you will make this call merge all, you will make n log n calls of it. So, that gives you the time complexity, okay, of n log n. And actually you can improve it by saying there is nothing sacrosanct about singleton list. You could actually take, suppose I start with the list 2, 3, 4, no, I shouldn't, 55 dot dot 55, 54 all the way to 45, let us say, and then I will go from 56, 57 dot 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 85, let us say, and from there I go to 84, 83 dot 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 60, let us say, and then again I go up and do some, I don't know. So then I suddenly switch and I go from 100 99 dot 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 86, let us say. I have a list like this, okay. Then I don't need to start with singleton list. Rather, what I can do is I will recognize that this whole thing is in reverse order, 55, 54, 53, etc., etc. So I will go and take, I will figure out what is this descending, I will figure out segments that are descending or ascending. Okay, this is a descending segment going from 55 all the way down to 45. So I will take the descending segment and reverse it, that becomes automatically sorted. So I will have 45, 46 dot 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 55, and then I have an ascending segment. So I will take 57, 50, 56, 57 dot 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 85. Then I have a descending segment 84. In fact, it starts from 85 itself. So I can put 85 either as part of the ascending segment or the descending segment, doesn't matter, or maybe 85 is alone. 85, 83 dot 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 all the way down to 60, but I have to reverse it. So if I reverse it, then I will have 60 all the way to 84, and then I have 100 all the way down to 86, which is a descending run, as it's called, down run, as I say, it's a descending segment, and I take that and I reverse it, I will have 86 dot 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 100. Now instead of starting with 100, whatever number, 55 to 45 is 11, 56 to 85 is 30, so 41, 84 to 60 is 25, so 66, 100 to 86 is 15, so 81. So this is a list of length 81. So rather than starting with 81 singleton lists and doing this merge, I am starting with 4 lists, that's all, each of which are already sorted, and my task is much reduced. You see, I don't need to make log n recursive calls, I just need to merge these 2 pairs, those 2 pairs. I will have 4 lists, I have 4 sorted lists, then I will have 2 sorted lists, then I will have 1 sorted list, and that's my overall sorted list, right. So this is very, very clever, and in fact this is the built-in okay. Haskell, I think you might have to do data.list, you might have to do import data.list, and this sort is a method that is provided by Haskell. as part of its libraries, and that is this very clever sort, okay, where you start with not singleton lists but with these upruns or reverse of downruns, okay, they will all be sorted and then you just start with them. And so this is very, very clever. So for instance, if I started with a list consisting of 1 dot 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 10,000, this is a very good exercise. Suppose I want to do m sort prime of 1 dot dot 10,000. You see that it takes some time. Sort, which is built in, of 1 dot dot 10,000. Okay, so I'll have to import data dot list. Is much quicker. You won't appreciate the quickness unless I try length of let's try 1 lakh. Yeah. Yeah, this is much quicker actually. Let me show it again for you. Length of sort of 1 till 100,000 is immediate. Length of m sort prime of 1 to 100,000 takes a little while, and if you increase the number, you will see that the differences are even more stark. Not too stark, but still. Yeah. So you see that it's still an order n log n algorithm in the worst case, but if your lists contain lots of runs like this, either totally descending segments or totally ascending segments, then you can actually make it much quicker. Okay. So that is it about merge sort. It is good to know all these things. It is not that you will be tested on the minutiae of merge sort in this Haskell course, but one of the aims of this course is not just to teach some Haskell programming, but also to teach you some basics of algorithms and reasoning about programs, and also about figuring out how much time programs take, and to teach you some fundamental algorithms. Merge sort is a fundamental algorithm, and this is a very nice implementation of merge sort. So now I'll move to a different topic. Once again sorting, but this is a different sorting procedure. Okay, so before that, just defining what an uprun is and a downrun is. An uprun is a maximal contiguous segment sorted in ascending order. A downrun is a maximal contiguous segment sorted in descending order. Okay.